the total area under the curve. When we define some margins, what will be the area that, those are things we discussed yesterday. Did anybody find anything additional to this? Did anyone get any additional information? So we have seen this blue shaped curve yesterday in the last slide, and it is defined by the function Gaussian distribution formula is given. Normal distribution formula is given on the right hand side, and from the area under the curve we can get what is the probability of getting a particular data in this entire data set. If at all a data point is far beyond the lower limit of this one, then we will call it as outlier, do the Grubbs test or Dixon's test and take a decision, go ahead. If the data point falls within this blue shaded region, we consider it as a part of like your own entire set of measurements. And we have seen that when you define one standard deviation on either side of the mean, the area covered by that shaded portion will be 68.3% of the total area. If you move two standard deviation, 2 sigma on either side, it will cover around 95.4%. If you go further 3 sigma on either side, it will come out to be around 99.7%. So these are all properties which we have mentioned, listed here. Those we will utilize, and once we have particular set of measurements, we can predict whether the next measurement which I am going to do, what will be the probability of getting a particular data point. These properties we will be using. And generally the standard deviation is the determining factor regarding the width of that probability distribution function. If your standard deviation is good, means small value, the width will be small. If the standard deviation is larger, that means poorer precision relatively, then you will see the curve with a larger width. All our efforts are to minimize the width of the curve. This general form of the Gaussian curve, where you plot the mu as the center point and sigma on either side, plus sigma on the right side when you are facing the curve, minus sigma on the left side. So if different people have different set of information, what will happen? Depending on their sigma, the curve will have either narrower or broader visibility. If the curve is broader, that means your standard deviation is inferior compared to the other one who has got a narrower curve. Here two curves are given in this picture, A and B. Is it visible to all of you? It is obvious that A has got better precision, narrower curve. From this you can make out that A's values are much closer to each other. They have got better precision. These values are spread through larger extent. However, B will be encompassing larger area. That means the probability of getting the true value using the B curve. The probability B curve is encompassing larger horizontal region. You see the base of those two curves. A curve is almost nearing the horizontal axis at a narrower range. We will define these things again. You visualize deviation from the mean. If the mean is at a particular maximum position, x minus mu normally for population parameters, we use Greek alphabet. Yesterday we discussed. So x minus mu is taken in the horizontal axis and the relative occurrence, relative frequency is plotted in this graph. So here you can see that each of the experimentalists will have different type of curve depending on the standard deviation. If you want to normalize them, what you do? We make the base same. If you divide by the standard deviation of the population sigma, then you get the value x minus mu by sigma, which we call as z parameter. It is called as standard normal parameter. The terminology is like that. Once you change the curve from x minus mu to x minus mu by sigma on the horizontal direction, y direction remains the same. You will see that all the curves will club together. It is normalized. Then what will happen? You can define any such set of measurements by a singular curve. This is the shape of the curve we discussed in the previous slide, normal probability distribution curve. The property of that Gaussian function we will be using to understand random variations, random errors. We have discussed three different types of errors, isn't it? Gross, systematic, and random error. Gross errors are visibly falling outside. Gross error will cause the result to fall outside from the other set of data. You can pick it out or you can do the Grubbs test or Dixon test. Systematic error, if it is present in your measured data, you can verify it by doing the checking by control sample analysis, quality control sample analysis, or you can use take help of your friend or some other procedure. Like that, there are methodologies which will help me out to correct for the systematic error. Random errors are still there, so we are trying to minimize the random error, minimize the width of that curve. That is what we are trying to do. So in order to make generalizations, what we do is we take the normalized function, standard normal function, which we call as z, x minus mu upon sigma. This is the generalized function for defining that. From the property of the Gaussian distribution function, we have seen that the area covered by 1 sigma on either side. When you take x minus mu by sigma, the integral will have limits from -1 to +1 for 1 sigma. Then we have already seen that it is 68.3% of the total area. Then you change the limit from -1 to -2 and the upper limit from +1 to +2. That is -2 to +2. Then the area will be 95.4% of the total. You can do the integration also and come out with the same result. The blue shaded regions in all these three curves show the area covered by the respective integral. And when we have limits of -3, by this safe or vacant, some particular discipline people are not there. Lab. So when we have the limits of z from -3 to +3, then the area is larger. Larger areas are covered. The idea is to reduce the area, defined area, and bring the maximum number of measurements within a narrower range so that your data is reproducible, like all repeated measurements are falling within small belt. But however, we will definitely have width. Natural width will be there for any repeated measurements, provided it is a continuous variable measurement. These are the different types of representation of this normal probability distribution function. If you go to refer to any Google or any website or any textbook, different types of representation of this normal probability distribution curves you can see. The first one is the area, the first figure. Pointer, if anybody can help me to take the pointer. Otherwise, let me see if the mouse works. The top leftmost figure. Otherwise, I will tell you the figure position. Top left figure you see almost the entire area is covered. So the entire area, that means the total area covered by this function will be 1. The total area covered, there is nothing special, and the rest of the graph is kept blank. Now we are speaking about this curve. The entire area is shaded. If you see some statistics text references, you will see that. Why is it not working? Rakshak, not showing. Pardon? Pushkar. Anyway, let it. This right side curve. In the right side curve, you see the lower half. We have already seen that the curve is symmetrical with respect to the mean or the center portion or the peak position. The left hand part full is shaded. That means from minus infinity to 0, z value, the integral, if you are to read through, the integral is written z values from minus infinity to minus infinity to 0. It is shaded. Similarly, if you see the right hand part of the upper figure, where the right side of the bell-shaped curve is shaded, the shaded area is represented by the integral from 0 to plus infinity for z value. Z equal to 0 to plus infinity. All of you are able to follow this much, na? The shaded area is represented by the corresponding integral which is given inside the figure itself. In the lower figures, there are different types of representations. First one is the total area. Second one is lower half. In the second one, the right part is upper half shaded. In the figure on the lower part, there are two, A and B. Everything is written there. I'll read it again. In the figure A, in the lower part, you see some portion is shaded from starting from z equal to 2 to the rest of the thing. So the shaded region represents the integral corresponding to z equal to plus 2 to infinity. Similarly, if you shade the lower one, lower tail, this part we call as tail portion of the curve. The lower portion of the, if there is a mirror image of A part, then it will be z equal to minus 2 to minus infinity, isn't it? And the B part of the lower figure, that is a confined area from z equal to 0 to 2. Is it clear to all of you? There are different types of representations. If you are referring to any like website, you have to see which portion is shaded in this curve. Now from this Z probability distribution function, we will be predicting a future measurement data. How we will do that? We will have exercises after this. For that, we have to understand what the shaded portion defines. Now we understood. If a particular portion partially it is shaded, what does it represent? Okay. We have understood. Now, if one particular portion is shaded, in all of these figures, the blue portion is shaded. In this figure also, right side, there are some questions for us to do. Now, let us try to understand the table of Z probability distribution, which will help us to take decision regarding a particular data is due to random error or not. That we will do some exercises today after this discussion. For that, all of us should try to understand how we have to read this table. Anybody knows how to do this? Some of the biology people might have already done this. No? Has anybody done this through? If most of you have not done, we will start from the very beginning. Okay. In this, we have a figure on the top portion, which all of us are now equipped to read. The shaded portion says that the area covered by that region from z equal to 0 to some particular value between 1 and 2, isn't it? It is neither 1 nor 2. It is some value z equal to 1.25. Is it visible to all of you? Z equal to 0 to z equal to plus 1.25. That area is shaded. Now we have to find what is the area corresponding to this particular region of Z. What we have to do is correspondingly we have to read through the table. In order to read the table given down, the leftmost column colored as yellow for us to have visibility, those are the Z values. Okay, leftmost values start from 0.0 to 3.4. We have seen that the shaded region is up to 1.25. It is written. Now we have to come to that point where the Z value corresponds to 1.25. Whereas when you read through the leftmost column, Z has got only one place of decimal value up to 1.2. Once you have reached that portion, now we have to go ahead in the, like what we do in the logarithmic table. Logarithmic table also we read like this. Now the second decimal point for Z is given on the right hand side row, yellow shaded row on the top. The second decimal, for example, it is 1.25, 1 to like 0.00, 0.01, like that. The horizontal row is given on the top. There we have to go to that place where the 0.05 lies. We have come 1.2 up to 1.2 value of result. Now you have to go to 0.05. All of you got it? How to read it? So when you come to 1.2, the area corresponds to 0.3849, isn't it? When you come to 1.2, it is 0.3849. Once you go to 1.25, it will correspond to 0.3944. All of you could get that value? All of you could get, na? If you could get up to decided, then try to do these ones. Area, the shaded portion corresponds to that particular region defined by the limits of the set. Now, all of you may try these 5 questions to find the area corresponding to these defined limits. Outside the limits of, first question is to find the area corresponding to the outside limits of plus or minus sigma. This curve gives us mu plus sigma. That means mu plus 1 sigma. So the Z value will be from Z equal to 0 to 1. Okay. Mu plus or minus sigma means plus or minus 1 sigma. Z value is from 0 to 1. So corresponding to Z equal to 1.00, what is the tabulated value that you have to measure? And since it is on either side, multiply with 2, then the total area is 1. 1 minus the sum of like this multiplied value. What you have to do, you have to go to 1, read the table 1.00, multiply it with 2. Why multiplication? Because you have to see on either side. If we are referring to this sort of table, if it were the other different way of representation, then you have to see. This is one-tailed representation with shaded portion corresponding to a defined margin. Sometimes it will be one-sided tailed representation. This one is shaded representation. Corresponding to 1.0. Could anybody reach? Like it is easy to read. If you do first one, second and third one is almost similar way. If anybody wants my help to read through, I will come. You can raise your hand. Z equal to 1. You have to read that. First question, that is that. Are you able to see this thing? Okay. The Z values you have to fix now. Once the Z value is fixed, corresponding areas are given by the black font color digits. Areas are in the black font color. Others are also black, only this thing without background. Without background. Z values are given with yellow background. Once you read that plus or minus sigma from the mu, that means you see this is only right side shaded one. Mu plus 1 sigma. Plus sigma means 1 sigma. So correspondingly Z value is 1. Mu plus 1 sigma. We have defined Z as x minus mu by sigma. So if you have to calculate Z value from this, it will be 1 for the first one. You have to read the corresponding value of the area. That will be 0.3413. You have to first find out what is the value of Z. Now you have understood it is 1. So leftmost ones are Z values. Leftmost ones are Z values starting from 0.0, 0.1, 0.2 like that. For 1.0, the immediate right side column that will read to 1 point. The second column topmost yellow base rows are there, na? Yellow base rows. Those represent the second digit of Z. Okay. If you have some digit after 2 digits after decimal, then you can 1.01 or like that. So now that it is plus or minus 1 sigma, it is 1.00. Okay. Then 1.0 corresponding to the first column. It will be 0.3413. Okay. All of you understood. If I ask you what is the value for 2.25 randomly, anybody can tell me 2.25. What will be the area covered by the value of Z? 2.25. If you have understood that, if you can tell me the value, 2.25. 2.25. 2.4798.
0.487. 487.
किसका अच्छा आईसेट है ओ बोले 4798 48 which one? Let me go there. नहीं तो उंगली रख के देख लीजिए 2.25 ना 2.25 okay 4878 yes. So that means you have understood. Did all of you get that value for 2.25? So good. So now that you have understood how to read the Z table, then the other things also you can do. When it is from plus or minus 2 sigma, beyond that, outside the limits of plus or minus 2 sigma, it is much easier. Once you have understood 2.25, how to read it, the rest of the things you can do. The third one is plus or minus 3 sigma. Understood? So all of you could read through. Yes? Very less. बहुत ही कम होगा. It will not reach up to 0 actually. There will be very, very small value. The value will be almost nearing 0, but not 0 exactly. This because probability distribution, probability will like, that is why I have written the word asymptotically in the beginning. It almost touches, but never. It seems like touching. That is why the infinity limit is almost. It depends on कि हाँ आप इसमें करेंगे तो हाँ yes. Almost it will be near to 0. All of you could do, na? Then the fourth and fifth one also you can do. Only the wordings are same. आपको भी समझ में आया ना सबको? So then the fourth and fifth one also you do. Here the limits are, in the first three, the limits were symmetrical on either side. In the third and fifth one, we have minus 0.6 sigma on left side plus 1.3 plus 1.3 sigma on the right side. Yes.
This question,
Fifth question.
it has to be mentioned like minus 1.50 sigma, because other than that, it
Yes,
means
yes, 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 yes,
this
yes.
sigma means
Which one? When you define z, z is x minus mu by
by
sigma.
Sigma that defines that.
Sigma, when you say z, it is normalized with the sigma. Then it is not required.
So you don't
It is
need-
not required. It is not typing, so it is not required. Then you say z. Yes, because you see the figure, z values are from minus 3, minus 2, minus 1 like that. There is no sigma in that. Yes.
What is new?
Mu is a population mean. Yesterday we defined this in a sample. Which one? Then we are taking the difference of our value minus mu, x minus mu. When our value sits on mu, the difference becomes 0. X minus mu becomes 0. So z is defined as x minus mu by sigma. So x minus mu is 0. Then whatever you divide, the point is 0. 0 by anything is 0. That is why this curve is called normal probability curve. Whichever person does, whichever set of people does, the curve shape will be same. The curve's scale will be same. Everything will be same. So that without looking at the actual data, I can predict. If you give me this like information of the set table and your set of data, how many set of measurements you have done, then I will be able to tell. We will do one numerical also after that. You understood where from the 0 has come. X minus mu. Mu is population mean, and sigma is population standard deviation. Yes.
Subtract from 1 for the whole.
Yes, yes. For the first three questions, we have to calculate the area, then subtract that area from 1. Only if you see this type of representation of the figure, in the previous slide, I have shown different types of representation. Some tailing, some center portion, some left half, some right half, like that. This is the one we are discussing in the class. If you go to Google for set table, you will see different types of representation. Here, right side, one particular portion is shaded. Left side also similar, it will be there if you take minus value. Isn't it? Then 1 minus you have to do. I will show you the results, answers. Shall we see the answers? If you have done, all of you have done, all the 5. If anybody has completed, you can cross check. In similar way, we will try to understand other statistical tables also. If you are asked to do similar type of numericals in the exam, this table, the relevant portion, like some additional portion other than whatever is required, the table, the relevant part will be given in the question paper. Only thing is that you have to know how to read through that table. Okay. If you try to understand the table, if the rightmost part, the right half part is fully shaded, then the Z value might have been reaching that level. The end point in the area, 0.4998, would reach 0.5. 0.5 is the maximum value when for a right shaded curve, normal distribution, half shaded curve, right or left, whatever. Has everyone checked your values? Done? If you are comfortable, then try to do this one. An object is weighed using a balance with known sigma. The measured weight is 10.002 gram. What is the probability that the measured value will be equal to the true value? That means x minus mu is 0. Now that you have understood how to read the table, this one you can do. In order to do this similar type of numericals, first you have to calculate the Z value, then go to the table, take the help of the table and read through the area. Now we are having the Z value, getting the area or the probability of getting some particular value. Probability of getting a particular value. That will be defined by the area covered by that particular region. Okay. Once we are compatible with this one, then from the area how to retrieve the Z value. That also we will do. If you have done, you can done. Mu is the true value. What is the probability that measured value equal to the true value? Measured value equal to the true value. So 10.002 equal to the true value. That is the mu. Yes. Measured value equal to the true value. X minus, we have to calculate Z. Mu. That is it. Go to English. That is the English. X minus mu is 0. That is X minus mu is 0. So Z is 0. Z is 0. Probability. You want to see the table, na? Having calculated the Z value, it's not moving backward. Shak hai kya udhar? To go backward, under. Z is equal to 0. You see what is the probability? When the Z value is 0, you read the table. आपको दिखो Z equal to 0. What is the probability? किसी को दिख रहा है? What is the probability for Z equal to 0? We have seen that the measured value is equal to true value. X is equal to mu. X minus mu becomes 0. What is the value of area? Z is 0, na? X is equal to mu. So X minus mu is equal to 0. Z is X minus mu by sigma. That means Z equal to 0. You agree? What is the area corresponding to Z equal to 0? Area corresponding to Z equal to 0. What is it? 0. 0. That means the probability that measured value equals true value, the probability is almost 0. It is very, very rare chance that you land up in the true value when you do the measured. This question. The other, which one? Previous one. Actually, वो slide ये नहीं हो रहा. It was not moving back. This question, if you are doing, if anybody has doubt in the previous one, now it is moving. This one, all of you have done now already. When the measured value becomes equal, when you are proposing that I got a true value in the first hit itself, the probability is very, very small. You are telling lie. Very, very rarest chance है कि you reach up in the goal in the first hit itself. This one you can do. Now the question is slightly modified. Same sigma, measured value is also same. If you want to find out the probability that the difference between the measured value and the true value is within a defined range, First you have to calculate Z, then go for the table. Then, all of you have done? Calculate Z value, go for the table and try to take out the area corresponding to that particular value of Z. Now that all of us have understood how to read the Z table, na? It is corresponding to 3.0. समझ में आया आपको? Sir? And this figure will give you right side shaded portion only. Similarly, on the left side, the band is from -3 to +3. So you have to do multiplication of 2. Okay. So it will correspond to 0.9974. 1 is the total area. If you represent in terms of percentage, it will be 99.74%. If your sigma is very small, 99.74% of 90, say 100 measurements you are doing, 99, more than 99 times you will be having the value within that small band. That is what it conveys. So all statistical efforts will be to minimize that sigma value, or if it is less than 30 number of measurements, minimize the value of S. Shall we go ahead for the next one? A manufacturer supplying glass electrodes. He is advertising that his electrodes have an operating life of 8,000 hours with a standard deviation of 200 hours. What is the probability that a given electrode will last for more than 8,400 hours? So if we are purchasing some instrument with some like fluctuation, given fluctuation, what is the probability that whatever you measure the data will be larger than some set limit, some threshold limit, or some lower than some lower limit? Using this type of calculation, we will be able to conclude whether the instrument data will have span of this range or even narrower range. If you can do at least one of the 3 subparts, the other ones will be almost similar. If you can do at least one for more than 8,400 hours, what is the probability that the electrode will last for so much hours? Once you do that part, the rest ones you can like have a check at hostel itself. First you have to calculate the value of result, then go to the Z table, read through that one. And this is an upper limit only, so right hand shaded one, directly you can subtract from 0.5. 0.5 is the total area corresponding to the upper part. Has anybody calculated result? It is not a big deal to do the Z calculation. Has anybody done Z? Done? The same value? X minus mu by sigma. X is 8,400, mu is 8,000, sigma is 200. So Z is equal to 2. If you read the Z table, it is 0.4772. Then probability will be area under the curve corresponding to that part of this curve, which is obtained by subtracting this value from 0.5. Got it? If you have done, which one? Done? Second one. Pardon? Second. Second key probability be 2.28. Yes. And then you are smart enough to do the like third is done. Na? Third key. Once a subtract. Correct. Once you have done first, na, second is almost similar. Third one is 1 minus sum of these two. Has all of you understood this? How to read this, na? The table and do the comparison. Now you are like confident enough. If the manufacturer says that my electrode is good, so and so good, then you can get assured key means at hand. Now, with 95.4%, we can tell that the electrode which he is selling will last at least for 7,600 hours, and it will not be working beyond 8,400 hours. That sort of conclusions we can make. If I say that I have prepared some new compound with the protein content 104, and like that, if I am giving the sigma value, from these whatever statements I make, you can make a judgment of my statements, whether I am exaggerating my data or not. So if we give explicitly such sort of results, the other person can make a judgment regarding the quality of our data. Yes. That I told you, there are different ways of representation of the result probability function. Herein we have shown the curve as shaded from the upper part. We have seen that the curve is symmetrical with respect to the midpoint. And here the portion is shaded for the upper part corresponding to define the Z value. Starting from Z 0 to Z equal to 1 point something, 1.25. If you shade the rightmost part fully, it will correspond to 0.5, isn't it?
Right.
Isn't it?
Till
So
infinity is the point.
yes, 0 to plus infinity, 0 to plus infinity, 0 to similarly 0 to minus infinity also. This is one particular type of representation. In some other representation, they will show you the tail one. Accordingly, first you have to see which table I am referring to. Okay, that is the most important thing. Then once you are comfortable reading this type of representation, you make sure that whatever data you are taking from Google or any other search media, what type of shading they have done. That is the first thing we have to take care of. Then read through the third value. If it is symmetrically shaded with respect to the origin, you need not have to go for 0.5. Directly you can do subtraction from 1 if it is outside the limit. If it is within the limit, take the value as such. Similarly, for the second part of the question also, you get the same value. Third part will be the difference between 1 and sum of the rest of the two. Now we have understood 5 minutes I will take. Now we have understood what is the significance of random error. With the help of random error, we could make judgments regarding the quality of the results, and if at all we are buying a product with certain declared sigma value, whether his or her claim is correct or not, that much judgment we are able to do since we know how to utilize the Z table. We have the sigma value, we have the corresponding reference mu value also, then we can do it. And as we have repeatedly discussed, the true value is most of the time not known to us. What we can do is to reduce the width of that curve, the random distribution curve, so that your confidence level with 95% for percentage confidence level you are talking, the Z value, you can narrow down the width of that normal probability distribution curve. So there lies our skill of experiment. How narrow you are able to do. So if I see the data set of 2 experimentalists, I will try to see who is more skilled just by seeing the distribution, normal probability distribution. I can make out regarding their performance or skill. So it can be extended further to state that with 95.4% confidence level, we can say that the true value will be lying in this region. True value will be lying in this region. If I want to say with 99.7%, we are extending 3 sigma on either side. That means we are expanding the baseline. If we expand to infinity, we will be 100% confidence. True value will be lying somewhere in this large set. So if you say that I am 100% confident, in statistics, I mean that your precision is very, very poor. But if you define with some say 68.3% confidence, then I will be feeling that yes, you have some defined belt of region to talk about. So 100% confidence in this parlance is not a good term to use. Define with a fractional confidence percentage level. Now your question will be, what is confidence level? Generally 100% confidence is good. Na? Confidence level, confidence interval, confidence limits. We'll just have these 3 terms known, then we'll solve. The curve, the probability distribution curve has got a like peak shape, na? Bell shape. This curve is called bell shaped curve. The base, the lower limit to the upper limit, the base value, horizontal axis value, that we call as the confidence interval. Confidence interval, starting from minus z to plus z, whatever value. In the previous question, we had defined minus 2 sigma to plus 2 sigma like that. That is a confidence interval. Then we are plotting the curve with reference to z value. And the limits, boundaries of confidence interval, those are called confidence limits. That point, particular point, that is confidence limit. And the area covered by the curve corresponding to this set boundaries, that is called confidence level or the probability, okay, or the degree of confidence. Confidence interval, that will be a range. Confidence limits, some boundary lines on the horizontal axis. Confidence level or degree of confidence, that will be the area covered by that particular curve. So whatever we have calculated is the confidence level or the degree of confidence or the probability. We have calculated probability. And the z value and the confidence interval, those are given here in this table. X minus mu by sigma is z, isn't it? And the confidence interval will be defined by those boundaries, x plus or minus z sigma on either side for calculating the probability. On the rightmost column, you see for the mean value, the same parameters are defined. Only difference is sigma is replaced by sigma by root n. Otherwise, the equations remain the same. Denominator is modified. Sigma is modified, not denominator. Sigma is modified, like replaced with sigma by root n. Do anybody remember that when we did the error propagation rule, the standard deviation of the mean was s by root n. Root n, 1 by root n times that of the individual value. From that error propagation, this has come. Okay, so that means whatever we have discussed in previous lectures, some or other we will be using in the coming lectures also. So once you have understood all these things, today's class, I think all of you could follow. If so, you try to do this one. The slides are downloaded in this download folder. You can do. Otherwise, I shall send you today evening, just after going to office. All of you may require the set table. You can use either this one or any Google reference you can do. Try to find out the confidence levels corresponding to these different values of Z. This is very simple to do, na? The answers are also given here. Should I send the answers along with? Shall I give one more exercise for you to do? The answers are here. This we will discuss tomorrow. This one already we have done. This numerical, this is not numerical. This is your comment regarding the, we have discussed accuracy and precision. Slide number 15 and slide number 13. Do this numerical, and in slide number 15 you have different curves for your comments. Slide number 13 and slide number 15. If you have time, try to do those and come tomorrow. From 13 onwards, we will discuss. Let it be there. If anybody wants to write down from